Alright gang, welcome back. Alright, we're up to the final stretch on this particular lecture here. We're going to be talking now about how we can use that information to figure out what the climate of the future is going to be. We're going to take the greenhouse gas emissions that are computed as part of all these different IPCC storylines and scenarios, and we're going to use them as boundary conditions for the input to these climate models. Then we're going to run those models out for 100 years or 250 years or 1,000 years or whatever it's going to take to give us the information we need, and we're going to get information from them like on each year along the way, what was the global mean temperature. And we have that kind of information right here on this diagram here. Now, one thing I want to point out right away on this diagram is that strangely this diagram represents these temperature changes in terms of temperature change since the year 2000. A lot of times we've seen things that was expressed in terms of like temperature change since the Industrial Revolution or something like that. To make it a little helpful here, I've actually put as in red the 0 line so that you can actually see, okay, this is warming since the year 2000 on there. And of course, in all of these climate scenarios, over the course of the next 100 years, the temperature continues to increase because, of course, the amount of greenhouse gases in the atmosphere is increasing. In fact, if you take a look at the year 2100, there's a range depending on which scenario we're talking about, and obviously there are more scenarios than this. This particular version of the figure only has 3 shown, but in general the scenarios fall in a range of 1.8 to 3.6 degrees Celsius of warming between the year 2000 and the year 2100. That is a great deal of warming. And just to show you, by the way, that that is due to the things that we are doing at this, continuing to do into the 21st century, the pink curve on there is showing the committed warming, where that is how much warming there would have been, in the next 100 years or whatever, if we had just stopped emitting greenhouse gases in the year 2000. So that's the committed warming due to the greenhouse gases that are already in the atmosphere, and you can see there's all this additional warming in the future, even in really optimistic scenarios like B1. And actually turning to B1, I want to show you how the right part of that diagram works. See how there's a column of that diagram that's for B1, and there's sort of a darker little place. That's sort of the best estimate from the range. Remember, a whole bunch of different research teams around the world ran their climate model using the data from the emission scenarios associated with B1, and so we have a type of ensemble here, where we have a large number of models, all with slightly different resolutions and different approximations to the 7 primitive equations and so on, and together they give us a sense of the range of possible outcomes. You'll notice that that's kind of what those lighter than blue parts on either side of the dark blue part is. That's the range of outcomes from all the models. You'll notice that they all say about the same thing. Yes, there is some uncertainty in the B1 scenario. Maybe it could be as little as 1 degree of warming. Maybe it could be as much as, I don't know, about, what is that, about 2.5 degrees warming or something like that. But none of those computer models were showing cooling. None of them were showing merely 0.5 degree of warming. It gives us a sense, this ensemble modeling strategy gives us a sense of the range of possible outcomes by the year 2100. The question becomes then, what about beyond the year 2100? Well, that gets a whole lot harder because we don't really have very good knowledge about what we can expect about the kinds of economic and demographic and societal and technological changes that we're going to see that far into the future. It's very difficult to make a meaningful sense about what we are and what we're going to do. But here's the deal. There's going to be people there, hopefully. Hopefully there's going to be people in the year 2100, right? And therefore, it's probably not going to be me, but it would be my kids, my grandkids, and it's going to be your kids, your grandkids, and maybe even you. And those people are going to wish that we had been thinking about them. And same with the year 2200 and the year 2300. We need to know. We need to be able to see how what we're doing is going to have the potential to affect their lives. But it's hard, because we don't really know very much about the future at all. For example, will we still be burning fossil fuels? That almost sounds silly. How? Surely by long before the year 2100 we're going to run out of fossil fuels and we'll be using green power and so on. Well, maybe yes and maybe no. It all depends. By the way, if you do a Google image search on space age oil derrick, you get the weirdest result ever. I have no idea what that thing is even supposed to be, but it does look like oil platform of the future, doesn't it? Will we be using fuel, petroleum and so on in the future? Well, we might. We might not. You possibly have heard of this idea of peak oil. Peak oil is this hypothetical date, and probably the future, in which it no longer makes economic sense to burn petroleum as a fuel. The idea is that we early on burned all the oil that was easy to get to, and we are increasingly finding more and more difficult places to find oil, and eventually it'll just cost so much to get that oil out of the ground that it just isn't worth it. It doesn't make economic sense anymore. The green power sources will be better. Some people say that this is very far into the future. Some people say that this is right around the corner. There's often estimates that peak oil comes around 2025, something like that. Some people say we've actually already passed peak oil, that oil isn't entirely making economic sense anymore. That's hard to say. But there's a lot of reason to say that the idea of peak oil is garbage. Because one of the ways that we can use technology is to keep finding oil in harder and harder places and use technology to get it out of there. The classic example of that is the Canadian tar sands. Tar sands are kind of what they sound like. They're basically deposits of gummy tar filled with sand, but it's petroleum that's in there. And we have used technology in a way that we can now economically extract petroleum from tar sands. It didn't make economic sense in the past, but as we have fewer and fewer sources of oil that are easy to get to, techniques like fracking and extracting oil from tar sands increasingly make sense. There's this idea that there's like a finite amount of oil in the world, and it's all in these little reservoirs, and once, all these oil rigs in Texas have run dry, it's done. That isn't the way it works at all. There's oil everywhere. It's just a question of whether it makes economic sense to get it. If it's too deep or in too hard of rock, or the deposits are too isolated and you don't get that much from each time you drive the well, or they're in too deep of water or whatever. But there's oil everywhere. It's just a matter of whether you're willing to spend the resources to get it. Maybe peak oil will never happen. Maybe we'll just keep burning fossil fuels forever. That, of course, is a disaster, but it certainly is seen to be, at least at the present time, the path we're on. No matter what, no matter how we deal with the whole business of burning fossil fuels and so on, it's going to take a very long time for the natural carbon cycle to start removing the carbon dioxide that we have put into the atmosphere and get it back down to like pre-industrial levels or whatever. Now, the book actually uses some figures from a paper. I decided to actually go in and get that particular paper. I have that reference up there in the book, just so you could see the original versions of these figures that are here. And what it is this particular study, Solomon et al., 2009, 2009, they wanted to know if we let carbon dioxide concentrations in the atmosphere get to some level, like 450 parts per million or 650 parts per million, and then stop burning fossil fuels, suddenly we have a green energy revolution or something, how long will it take for carbon dioxide concentrations to return to pre-industrial levels? And that's what these diagrams are showing here. Now, the way they've labeled them is a bit awkward, so I'm going to put some colors on these diagrams here. But like, for example, the red curve on there now is if we let the carbon dioxide concentration rise until it hits 450 parts per million, and then, suddenly cold fusion, wind power, solar power, something, it suddenly becomes more efficient than petroleum, we just don't burn it anymore. Well, look what happens. We start going down quickly at first as the as like photosynthesis at first is able to uptake a bunch of carbon dioxide. But you know what? If you just get the carbon dioxide concentration up to 450 parts per million, even way out at the year 3000, we still haven't returned all the way to pre-industrial carbon dioxide levels. And 450 parts per million is nothing. We're already a little over 400, and remember pre-industrial was like 280. We're gonna blow right through 450. And if you pick one of these higher top peaks, like for example 850 parts per million, let's say we continue burning fossil fuels until we hit 850 parts per million, and then we suddenly have it's more economical to use green power or whatever. Well, it's true, a lot of that carbon is removed in the first 100 years or so, but even again, even out in the year 3000, the carbon dioxide concentration in the atmosphere is really high. That's a really big problem, because that means that there are these high high greenhouse gas concentrations for a very long time. That means that, we're going to be warming the planet for, at least the next millennium or so. And actually, we're nowhere, at the year 3000 in this model, we're still nowhere near pre-industrial levels. And that's why on the next part of the diagram from the Solomon et al. Paper, we start seeing what happens to global warming if we reach certain thresholds of how much carbon dioxide we emit in the atmosphere before we switch to a greener technology. For example, in this figure here, you can see that if we peak our carbon dioxide concentration in the atmosphere at 450, which is absurdly low, we're not going to be able to stop it by then, you can see that even then, the temperature, it's true, doesn't continue to get much warmer after that, and it does start tapering back towards normal, but even at the year 3000, we are still a degree above the pre-industrial. Holy smokes, this greenhouse gas, this is a very long time for these greenhouse gases to be in the atmosphere, and therefore a very long time we're going to have to deal with global warming. 450, we're going to blow right through that. How about the 850 parts per million curve? Alright, if we allow by about the year 2100 or something for carbon dioxide to hit to the 850 parts per million before we finally stop, the planet will have warmed up in that particular model about 3 to 3.5 degrees Celsius. Okay, that's in the range of what seems like it could happen. And look, I mean, 1,000 years from now, what would that even be? Your 50 times great-grandchildren will still be dealing with 3 degrees Celsius of global warming. Holy smokes, that is a whole long time that these planet problems go on and on and on. And the same is true of like the kinds of things that are consequences of global warming, like for example, sea level rise. Now, look at this one here. I'm just tracing there in red the one for peaking at 850 parts per million, and you can see sea levels rise, and they continue to rise over the next 1,000 years. In fact, the sea levels don't even start falling in that 1,000 years. Now, I want to draw your attention to an important point here too. This is only showing thermal expansion of the ocean. Remember we talked about the different reasons why the ocean might rise. This is not including things in this particular simple model like melting of ice caps and things like that. That is not, that would obviously be over and above this until of course we ran out of ice, and then we wouldn't be able to continue to have sea level increases due to melting ice. Man, that is something on the order of 50 generations that we're going to be dealing with this. And actually, I mean, you can see at the year 3000, we're still nowhere near getting back to normal. This is terrible. Regardless of how high the carbon dioxide concentrations peak in our century, the associated warming, like I see I have like a 450 and a 550 and a 650 on there, the associated warming goes on for more than 1,000 years. This is a big problem. There's a term in climate science for this. We say that the global warming associated with carbon dioxide in the atmosphere is described as being irreversible. And irreversible it's not quite means that. Irreversible doesn't literally mean like it'll never go back to normal, but it doesn't go back to normal for on the order of thousands of years. It takes until like chemical weathering of rock and things like that are able to flush all this carbon out of the atmosphere, and that's just going to take thousands of years, way longer than we can plan. That is not good, and it's all because of things we're doing in our time. Now we can make choices as to how far up that curve we're going to go. Okay? None of these outcomes are good. I don't like the idea that my 50x great-grandchildren are going to be dealing with this much global warming at the year 3000, but we can make it a whole lot better if we only let carbon dioxide get to 450 parts per million and not 850 parts per million. Other forms of global warming, other radiative forces are not necessarily irreversible, and your textbook talks about the fact that like global warming by methane is not irreversible. If we actually stopped emitting methane into the atmosphere, we would be able to get rid of the methane and return, if that was the only greenhouse gas, we'd actually return to pre-industrial climate within about a few decades. Methane is not a reversible, global warming due to methane is reversible. Global warming due to carbon dioxide is what we call irreversible climate change. Uh-oh. It's going to get bad. It's going to get worse. Wait to see future lectures where we're going to start talking about like what this means and how this is going to change our world. But just to finish up this lecture, let's do a couple quick questions. Question 6. Numerical climate models say that by the year 2100, Earth's global mean temperature will be about blank warmer than it was in the year 2000. 0.3, 3.0, 13, or 20 degrees Celsius. How much warmer is the planet going to get? Make a choice from these 4 options and get a little feedback before you move on to question 7.